The electric field. Physics, 11th grade. Minerva Bilingual School. Gracias, Lempira, Honduras, Central America. Let's do this. All right, guys, welcome to physics. Forgot to say class 80. It's class 80. I'm tempted to restart this video, but you can see that it's really late and I'm not going to restart it. So this is physics 11th grade class 80, 80. I think I forgot to say that in the intro, but that's okay. Let's do this. Okay. I hope you guys can hear me okay. I think you can. If you can't, say something. If you say something, I will not be able to hear you actually. So too bad for you. But I think that you'll be able to hear me okay. And I'll see you in the recording before I post it on YouTube if you can hear me. I'm going to try to make our classes more content focused. I know I talked about the coronavirus and flattening the curve last class in the class, class 78 or 79, whatever, class 79. But I'm going to try to make our classes more physics focused to not waste any time. If you guys don't want to hear about coronavirus, you don't have to. So let me make sure my pen's working. It is working. So guys, really quick review. You guys, well, we need to use Coulomb's law in today's studies of the electric field. Before we even talk about Coulomb's law, as an introduction to the electric field, let's look at some really quick real-world applications of the electric field. Real-world applications of the electric field.
According to Quora, electric fields are used in some painting. They generate a small charge on the surface of the material to be painted, and they generate the opposite charge.
Okay, thank you, Google. Also, guys, listen to this. Real-world applications of electric field studies.
According to Lumen Learning, electrostatics is the study of electric fields in static equilibrium.
So you guys can see that this mentions laser printers, inkjet printers, electrostatic air filters, photocopiers, all these things. So what you're learning is practical, and I believe that some of you guys will use this information when you become engineers. I did not say if, I said when some of you become engineers. So you're gonna have to learn it now or later, so might as well learn it now. So here we go. Let's learn about the electric field. It has a lot of content a lot of content in common with electric force, like we learned for the last few classes. So as a quick review, we're going to use this formula. So right here, I'm going to write the electric force formula. Electric force, we know, is equal to K, which is the Coulomb constant, times the charge of the first charge in coulombs, times the charge of the second charge in coulombs, all divided by the distance between the charges squared. Okay. Now let's make sure that we're all clear on units. R squared. Now I did not give you guys the units for the Coulomb constant last class, but I'm going to give you the units this time, today, because it's going to be important to our discussion about the units of the electric field strength that we'll be looking at in a few minutes. Okay, so the units for the Coulomb constant are actually newtons. I need to turn my light back on. Now the units for the Coulomb constant are actually newtons times meters squared. Okay, newtons times meters squared, all over coulombs squared. Okay, that will be relevant very soon here. Now you guys know that the units for each of these charges are coulombs, and the units for R is meters, but it's R squared, so it's really meters times meters, or meters squared, are the units that we'll be using there. Okay, now let's talk about some of the background for what exactly is an electric field. So the idea of an electric field is that we're going to draw right here a very big charge. And when I say big, I mean that it's actually the charge of this object that we're looking at, this circle, in this case, has a very high charge in the sense of coulombs. So I'm just going to put a lot of little pluses here. We're going to say this is a positive charge. Okay. Now, something that we have not discussed yet is that this charge actually creates an electric field around it. Okay. Now, the strength of the electric field depends on, number one, the charge of this charge in coulombs, and also it depends on the distance that any point is from this charge. Okay. So we're going to say that, let me draw this distance better. So we're going to say that there's a really small charge. I'm going to put it right here. I need to make it a little bit bigger. We're going to say that there's a really small positive charge here. Now, something that you guys need to realize is that this positive charge actually creates its own little electric field. Okay, but in order to use the electric field formula, we need to assume that the electric field that this little charge creates is, we say, negligible or ignorable, because technically, similar to, like, we know that Earth actually exerts gravity on the sun, but the gravitational force that the Earth exerts on the sun, we say is negligible. In other words, ignorable. In the same way, I have not shown you the electric field formula yet, but the force that this little charge exerts on the large charge in our situations, we're going to say is negligible, so we can ignore it. Okay. If we don't ignore it, then it gets really messy. And for this class, we're going to assume that the electric field created by this little charge is negligible, and the only electric field that's present is the electric field being exerted by the big charge. Okay. Now, next thing to remember before I show you the formula for electric fields, to calculate the electric field strength, is that if we have a very big charge, like this, if it's positive, we're going to assume that the electric field is repulsive. And for now, I'm just going to leave it at that. We could get into a lot more details about why we're going to assume that it's repulsive, but just for now, we're going to assume that it's repulsive on any point that we're talking about that's being affected by the electric field. In the same way, if I'm talking too fast, I'm sorry. I drank some coffee before this, and also what time is it? It's 11:57, and that is not AM, it's PM. So if I'm talking too fast, then, I just got kind of scared. I heard something. I'm on the roof of my apartment, and I thought there was an animal coming to get me, but there isn't. I think it was just the wind. So if I'm talking too fast, you can slow down the YouTube video. Okay, cool. Now, in the same way, if we have a very large charge that we're going to be calculating, if we have a large charge that's negative like that, we can calculate the electric field strength at any point that any point is experiencing around the charge. But if it's a large charge that's negative, unlike this, the negative electric charge is going to be, for our purposes, we're going to assume that it's attractive as opposed to repulsive like the positive one. Okay. Now, those two things I just told you, you need to remember that, because the problem for this class 80, is going to assume that you understand that a positive charge is going to be repulsive, a large positive charge is going to create a repulsive electric field. And the same way, a negative large electric charge is going to create an attractive electric field around it that's being exerted on points in space around it. Okay. Now, all that said, I'm going to tell you now we're going to go into the formula for electric field strength. Okay. So electric field strength is represented by E. Okay. Now, electric field strength is equivalent to the electric force, which you guys know how to calculate using Coulomb's law. Coulomb's law is what we've been dealing with, right? That's Coulomb's law. So electric field strength is equivalent to the electric force divided by the charge of a small charge we're going to call Q sub 0. This is divided by the charge of a small charge that's in the electric field. Okay. Now, when I say Q sub 0, this right here, what I'm referring to is the charge of that little point that's in the electric field. Now remember, the charge of Q sub 0 is negligible. So we're going to assume that Q sub 0 is not actually exerting an electric field on the big charge, because if it does, it's going to get really messy, and we're not going to deal with that in this class. There are ways to calculate that, but for this formula, we're going to assume that it's negligible. Now, here's where it gets really interesting. We're going to spread this formula out and really try to understand the units behind the electric field strength. So I'll just tell you right now, before we even start explaining the units of this, the units that we should have for the electric field are newtons. I'm going to go like this. I'm going to go right there. Newtons per coulomb, right? We know that electric force is newtons. And guys, there's like, I hear a dog whimpering, and I literally just got the chills because not because I'm cold, but because it made me. What is that sound? It's freaking me out. Stop making that sound. Where is that coming from? There's a dog, and he's going, I'm getting freaked out. There's a dog. I don't know if it's on another roof near here, and he's going like, like that. It's freaking me out. We know that electric force is newtons. We've talked about that. And the charge of a point charge is measured in coulombs, right? So it would make sense that if we have newtons and coulombs, that the units for electric field strength would be newtons divided by coulombs, right? That should be intuitive for you. But now I'm going to explain to you in more detail why that is. So let's flush out this electric force. We know that electric force, more specifically, is all of that, right? So we can say electric force is the Coulomb constant times the first charge times the second charge divided by the distance squared, right? Now that's the Fe, all that. So now we're going to go divided by Q sub 0 is I'm going to go Q, so we're all clear. That point is what we're referring to as Q sub 0, okay? The charge of that little tiny charge in our situation. I hope this is making sense so far. Some of it should feel abstract, and if it feels kind of abstract, don't be surprised, because that's just the way it should feel right now. We're going to get into a more tangible, somewhat quote-unquote more tangible example. We're getting closer and closer to quantum physics as we study the nature of electric force and electric fields and the way that protons and electrons behave. And the further that you move from, I'm going to go to the camera to explain this part to you really fast. Okay. The classical physics, much of what Isaac Newton gave us is what we would call like Newtonian physics. A lot of that is intuitive. For example, if I drop this electronic pen, I expect it to fall. And according to Newtonian physics, because of the when you calculate the gravitational force between this and the Earth, Newtonian physics explains that yes, this should fall, and it's the same way I expect it to behave. That's what I expect it to do, is fall. In other words, it's intuitive for me. Now, the further that you move from Newtonian physics toward quantum physics, which Einstein, among others, helped us understand, the further that you move from Newtonian to quantum physics, the less and less intuitive that the phenomena become. So, in other words, the further you move from Newtonian physics into quantum physics, the less you expect things to happen the way that they happen. But the reality is that quantum physics that Einstein helped, trailblaze is part of the reason why we're able to have computers. Because now we're getting into territory that I can only explain a little bit about, but I'll tell you right now that we have to understand the nature of quantum physics in order for our circuit boards to function the way that they do, and in order for us to store information in the way that we do. We have to understand quantum physics. So we know that it's not just a It's not imaginary, right? But when you study them, things happen the way you don't expect them. So if this content feels abstract, don't be surprised. Enough said. Okay, now let's talk about the units of each of these components that we just flushed out here. Now remember, all this is still equivalent to the electric field strength, right? I'm just writing it in a different way. So now I just told you guys that K, the units for K, is the newtons times meter squared divided by coulomb squared, right? So right here, I'm going to say, let me get rid of that arrow. It looks too messy now. So we're going to say newtons times meters squared divided by coulombs squared, right? Times, now the Q1 right here, we know is coulombs, right? And then I wrote Q1, right here I wrote Q1, and none of you corrected me. Thanks for nothing. I should have written Q2. Nah, just kidding. You couldn't correct me because you're not part of this video. Now, this Q2 is again coulomb, so we can write another C right there. All divided by R squared. This is meters times meters, right? So meters times meters is meters squared. So we can say meters squared. Meters squared. So now, it looks kind of messy, but I think that you're following me overall. So now all of this is the units for all of that, right? Okay, now watch this. The Q sub zero, sorry, that we just started talking about this class is still on the bottom, right? Q sub zero, and that's coulombs also. Okay, so now let's simplify all of this. If I want to say all of this divided by C, that's the same as saying all of this times 1 over C. Okay, so I'm gonna write that so it's easier for us to deal with. So we're gonna say, and also in this process, I'm gonna go multiply so that it looks a little bit nicer for our next step. So I'm gonna say Newton meters squared times C all over the C squared times meter squared. Okay, so C squared times meters. Guys, by the way, after you see all this happen, it's going to be crazy because, yes, algebra explains the natural world in such a beautiful way. Let me say one more thing. I don't think I've told you guys this before, but when you hear an atheist say they don't believe God exists, right? Ask them this question. Ask them, if God does not exist, then why does algebra, which is order, right? Algebra happens logically. Algebra is an example of a very logical process. Why can algebra explain the natural world? Okay. Right now, you guys, we're using algebra to explain the nature of electric fields. Okay. Now, algebra explains gravity. Algebra is the language that we use to communicate the concepts of gravity into the way that, and it's the language that we use to calculate the phenomena of gravity and all of physics. I'm not exaggerating. So if all of the natural world, or at least much of the natural world, the physical world can be explained through an orderly process we call algebra, then ask the atheist, how is that possible if it all happened by chance? Right? And they'll say something like, I don't know what they'll say. I don't think they can give you a good answer. So then you can tell them, and guys, when you go to university, you're gonna meet a lot more atheists, and you'll probably have these conversations, some of you at least. Then you can tell them the only way that the natural world the only reason that the natural world would be able to be explained through a logical process, through order, such as algebra, is because the natural world was created by an intelligent designer. Think about that. Anyway, let's get back to physics. Okay, we're getting close to being able to show you guys why the newtons per coulomb is the newtons per coulomb. That's what I'm getting to. So now let's let's not forget that we need to divide everything by c, right? Because that c, we haven't moved this c down here yet. Now, instead of dividing by c, I'm going to say times 1 over c. That's nicer. So now let's combine all this and simplify. Okay, so 1 times all of that is just all of that, right? So I'm going to go newtons meters squared, and then c times c, coulombs times coulombs, is coulombs squared, right? All divided by c squared times m squared times c. Okay, so these are capital C's. Some of them look small, but they're capital. C squared times m squared times c. Okay, now let's cancel whatever we can cancel. M squared is on top and bottom, so they cancel. M squared divided by m squared is 1, so they disappear. C squared divided by c squared cancels. What do we have left over? We only have the n and the c. That's where we get newtons per coulomb. Maybe I'm more excited than you guys are, but I think that's super cool. That's where we get the newtons per coulomb for electric field strength. Okay. Now, I'm getting close to being done with this lecture. Let's see how long we've been going for. It's been 21 minutes. I didn't tell you guys this before, but I will tell you that my idea for this class 80 is to explain to you more the theory and not too much practical calculations, because you've done a lot of the practical calculations that you need to know how to do in class 79 and all the way back until in class 73. You've been doing calculations that involve the superposition principle. Now, let me say a few more things. The example problem that your homework problem is, I'll tell you, I have my paper here to tell you what page. This problem that I'm going to give you guys for homework for class 80 is, you can also find as the example problem on page 574. Right? And that goes also through page 575. And you're going to have to use some of the trigonometry that we've been using in the past few classes in order to find your final answer. Okay, so you're going to make the rectangle like we've done before. And let's see, what else do I need to tell you before we look at the example problem? I'll tell you about rounding, the way that we're going to agree to round in a minute. What else? Yeah, I think that we're ready to talk about your homework problem. So I'm going to go to the second page here. Now, here's the problem that you'll be doing for homework tonight. I'm not going to do this for you. I will do this next class, and I'm actually going to call the next class probably class 80 solutions. And that's going to be on whatever day we have physics next. I would tell you, but I'm not in my room, aka office, because I'm on the roof of my apartment at like midnight, and I don't have the schedule in front of me. But whenever we have physics next this week, I think it's like, I don't know what day. We're going to talk about the solution of this. But if you want to have your mind prepared for this is probably going to come on the partial 4 exam. Then I highly recommend, and actually I believe, even if I don't say this, I believe that many of you will do this without me saying it. I highly recommend that you really try to get the right answer before our next class, because if you just let me do it, your brain is not going to develop in the way that it needs to be able to do this for the exam. Okay, because we can only practice certain types of problems so many times before we move on to the next topic. So with that said, let's talk about rounding, and then we'll talk a little bit about this problem. Now, just so we all agree, if you guys all round to the nearest hundredths, okay, I'm going to write that again. Round to the nearest hundredths. Okay. And you also use scientific notation in your calculator this entire time, then you're going to get exactly the answer that you see on what page did I tell you? Page 500, this example in the book, they go through their process and their answer. If you want to look at their process, you can if you want. I think that their process is more confusing than what we'll talk about next class. And I think it's more confusing than what you guys would be able to do yourselves. But if you want to look at their process and answer, the answer that they get after all their process is going to be, I'll tell you, it should be exactly what you get when you guys follow these parameters, round to the nearest hundredths and use scientific notation. And I know that because I did it like an hour ago, about an hour ago, something like that. And I got exactly their answers, like to the decimal. Now, let me specify one more thing about this process. Even if you get an angle, like let's say you're using tangent, inverse tangent, opposite over adjacent to find some angle in our diagram. And I will say that you guys will need to use both a distance diagram and a force vector diagram like we did in class 79. If the things I'm saying today, right now, are super confusing for you, I recommend that you watch the class 79 solution video again in order to kind of strengthen your knowledge base. Okay. Now, if you get an angle, like say in your calculator, if you're in scientific notation in your calculator, you're going to get like, for example, 5.7 times, we're going to say 5.738 times 10 to the 1. That's the same as saying 57.38 degrees, right? But when I say round to the nearest hundredths, I'm saying round, when I say hundredths here, I'm saying round from scientific notation. So really, if you're going to round this number and then in all your intermediate calculations, if you're rounding to the nearest hundredths, the number that you'll use is going to be 5.7. Now this 3 becomes a 4 because the 8, right? So 5.74 times 10 to the 1. Degree, I'm going to go degrees. If you got something like that, I don't think that you get this exact angle in your processes, but here's an example. Now we all know that this is 57.4 degrees, but here's the number that you should be using in your processes so that we can all agree on the same answer in the end. So there's that. Let's talk a little bit about this problem, calculating the electric field strength at a certain point, and then you guys will be ready, I believe, to do this problem and succeed and have your answers and your processes before next class. You don't need to send me your homework assignment before next class because that's going to come after we talk about the process. So just keep your homework to yourself until then. Now let's talk about this symbol right here really quick. You guys see that right there? That is the symbol for micro. Okay, micro. So if I have 7.00 microcoulombs, that's the same as saying 7.00 times 10 to the negative 6 coulombs. Let me corroborate that. What does how do I ask it? What does the micro prefix represent?
According to Wikipedia, micro is a unit prefix in the metric system denoting a factor of 10 minus 6.
Yeah. So when you see this number in your problem, this is the number that you're going to use in the calculator, 7.00 times 10 to the negative 6. Similar for this number here. Okay. So keep that in mind. I'm going to erase this part. No, I can leave that actually. I'll just erase up here. What else? Yeah, guys, I think that you are ready to this problem. Let me look at my notes to make sure there's nothing else important I need to tell you before we say good night and goodbye. What else? No, I mean, I don't want to tell you guys too much because I want you to really spend time thinking about this problem. And you guys, what I'll do is I'm going to write the answer here. The answer you can find in your book, but the answer that you should get for this problem, I'm going to write right here. Now, this is my answer. And again, I'm going to look at page 574 just to double check. The answer they get is 2.71 times 10 to the 5 newtons per coulomb is the electric field strength at the point in this problem. And remember, this is after doing all your trig to find the resultant electric field strength. And the angle they get is 66.6 degrees north of east. And that's exactly what I got. So here's the answers you should get for this problem. So we're going to say the electric field strength resultant equals 2.71 times 10 to the 5 newtons per coulomb. Okay. That's, if you move the decimal 5 places, that's 271,000 coulombs about. Now at 66.6 degrees north of east, right? So here's east, right here. So in that direction, the angle you should get is 66.6 degrees after doing all your trigonometry and electric field strength calculations, all that. So I'm excited to see how many of you get this answer exactly. And if you get it, and if you feel like email me sometime before next class and tell me that you got it, because that will make me so happy to hear that you got the same answer. Yeah, guys, that is everything. Let's go back to video. All right, it's everything for class 80. Yeah, it's everything. Peace out.